Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 9th, 2025. We're looking at an interesting ICLR conference paper titled Amortized Control of Continuous State Space Feynman-Kac Model for Irregular Time Series, published a little over 3 months ago. This paper introduces a new method, the Amortized Control of Continuous State Space Model, or ACSSM, for modeling irregular time series data, where data points aren't evenly spaced. It uses continuous state space models, which describe how a system's hidden state evolves, with their dynamics defined by stochastic differential equations, or SDEs. These are equations for systems with randomness. The approach then uses variational inference, a smart approximation technique, and ideas from stochastic optimal control theory to make it all work efficiently. Alright, so figure 1 here gives us a conceptual illustration of how this amortized control of continuous state space model works. We see on the left, it takes these irregularly spaced time points. Those are the O_Ts. An encoder, which is like a data translator, then maps these into what are called latent observations, sort of hidden patterns. These latent observations help determine a control policy, essentially a set of guiding rules. This policy, using a masked attention mechanism, a clever way for the model to focus on relevant data parts, then shapes the latent dynamics, the underlying continuous process. Finally, a decoder translates these learned dynamics into a complete output time series. Building on how the model processes data, Figure 2 illustrates 2 types of information assimilation schemes, basically how it takes in and uses the data. The top history scheme uses feed-forward networks, which are neural network layers that pass information in one direction, and that attention mechanism we talked about, to process data points mostly based on past information. The bottom full scheme, however, lets the attention mechanism look at all data points simultaneously. This full approach is key to their transformer-based data assimilation, allowing for more efficient parallel processing. So, we've seen how the model is designed for efficiency with approaches like that. Full scheme for data assimilation. Now, Table 2 here shows us how it performs in terms of accuracy, presenting the test mean squared error, often just called test MSE. This metric measures how close the model's predictions are to the actual unseen data, with lower numbers being better. The amortized control of continuous state space model achieves a test mean squared error of 2.98, and all these values are scaled by 10 to the minus 3, so they're quite small. This score is clearly better than other methods shown. Okay, so beyond that test mean squared error, Table 1 now shows test accuracy in percentage. This tells us how often the model correctly classifies new data, and higher is better. The amortized control of continuous state space model hits 91.4%. This is better than latent ODE models, which use ordinary differential equations, equations for smooth, non-random changes for their hidden states, and also better than latent SDE models, which use those stochastic differential equations we talked about earlier. It also just edges out MTAND, showing good classification performance overall. Following up on that strong classification accuracy, Table 3 now digs into the test mean squared error for interpolation and extrapolation tasks. Interpolation, that's filling in missing data points, while extrapolation is predicting future values. Again, lower test mean squared error is better, and these scores are scaled by 10 to the minus 2. The amortized control of continuous state space model shows really strong results. For instance, on USHCN, it achieves top scores of 0.006 for interpolation and 0.941 for extrapolation. It also performs very well on PhysioNet and is notably efficient, with runtimes around 2 to 4 seconds per epoch. Alright, so those strong test mean squared error results on tasks like interpolation and extrapolation are quite impressive. Now, Figure 3 here gives us a visual example of the kind of data the amortized control of continuous state space model works with. At the top, you see a sequence of pendulum images. These are the inputs, and notice they're observed at irregular time intervals. Below that, the 2 curves show the sine and cosine of the pendulum's angle over time. These are the regression targets, essentially the specific values the model is trying to learn to predict. This figure really highlights the challenge of handling unevenly spaced real-world data. So that pendulum example really shows how this amortized control of continuous state space model handles complex, irregularly timed data. In essence, the big achievements are its strong performance on tasks like predicting future values and filling in gaps, and its impressive speed. It pulls this off by using continuous dynamical systems, which model how things change smoothly over time, and advanced methods like variational inference, a smart way to approximate complex probabilities, all while being designed for efficient parallel processing. That's a wrap for this AI Research Roundup. I'm Alex, thanks for listening.